This is the most advanced object our species knows how to build. 80 billion transistors, $30,000. Right now, it's running the best artificial intelligence we have, for one person. And it is using 0.34% of itself. Not 30%, a third of 1%. 99.6% of the most expensive silicon on Earth is doing nothing. That's not a bug. Nobody is going to fix it with a faster chip. It's physics, and a lump of tissue running on 20 watts, about what your fridge bulb draws, does not have this problem at all. Let's find out why. Here's what an AI chip actually does. It's simpler than people expect. Take two numbers, multiply them, add the result to a running total. Multiply, add. Multiply, add. That's it. That is 99% of artificial intelligence. Every poem, every line of code, this one operation, repeated until the numbers start to look like thought. A modern chip does that about 1,000 trillion times a second. And here's the number that starts this whole story. One of those operations costs about 0.2 of a picojoule being a trillionth of a joule. The energy your phone spends lighting a single pixel for 1 second would pay for billions of them. The maths is free, essentially genuinely free. So if the arithmetic costs nothing, and the chip is doing almost none of it, where is all the energy going? To multiply two numbers, you need two numbers. One comes from your question. The other is a weight, one of the values the model learned during training. Think of it as one setting on one dial. A model like Llama 70B has 70 billion of them, and they have to live somewhere. They live here. This is the memory, and it sits a few millimeters from the processor. In computing terms, that's practically touching. But moving a number is not free. You have to charge up a wire, and the longer the wire, the more it costs. Fetching one weight across those few millimeters costs about 64 picojoules. 64 picojoules to deliver the number, a fraction of 1 to use it. Fetching a single weight costs more energy than doing 200 multiplications with it. Imagine a workshop where the worker assembles a part in 1 second, but every part is trucked in from across town. You could give that worker superhuman hands. It wouldn't matter. They'd stand at the bench all day, waiting for the truck. That is what a 200 billion transistor chip is doing, waiting for the truck. Engineers have a chart for this, and it's the most useful picture in the field. The flat line is how fast the chip can do arithmetic. The diagonal is how fast memory can feed it. Whichever you hit first is the one that owns you. Where they cross is break even. For this chip, about 295, meaning for every byte you drag out of memory, you need 295 operations, or the trip wasn't worth it. Generating text one word at a time for one person, you get one operation per byte. The truck drives across town, delivers a single bolt, and drives back. That is the 0.34%. So how does anyone make money doing this? Well, they cheat. And it's genuinely clever. If the truck is making the trip anyway, fill it. Watch. Same chip, same model, but now it's answering 4,000 people at once, and every weight that gets fetched is used 4,000 times before it's thrown away. Utilization goes from 1/3 of 1% to 67. Energy per word drops by a factor of 200. Nothing about the hardware changed. We just stopped wasting the trip. This is why a chatbot in the cloud is cheap, while the same model on your own computer crawls. At home, you're one customer. You get the whole truck, and you pay for the whole trip. Second trick, and it's quietly reshaped the industry. If moving bytes is what costs you, move fewer bytes. Store each weight in 8 bits instead of 16, or 4. The model gets slightly less exact, and for most purposes, it barely notices. Halve the size of every number, and you've halved every truck trip in the building. 3 generations of AI chips have been obsessed with smaller and smaller numbers. It was never about the maths, it was always about the shipping. And here's one you felt yourself. Every word in your conversation has to be remembered and reread for every new word the model writes. Push the conversation long enough, and this becomes the biggest cost in the whole system. That's why long chats get slow. The model isn't thinking harder, the truck just keeps getting bigger. Now, the only other thing in the known universe that does this job well, you're using it right now. You've heard the number, 86 billion neurons. Worth knowing it comes from one study that counted 9 brains. And a reanalysis last year argues that only supports a range, 60 to 100 billion. Either way, something like 100 trillion connections on about 20 watts. I want to be careful here, because this comparison gets abused constantly. The brain is not a better GPU, it's slow. A neuron fires a few times a second against a chip's 2 billion. It can't be reprogrammed, and it's running your breathing, your balance, and your eyesight at the same time. So we compare one thing only, the single elementary operation each one performs. The brain's version of multiply and add is a synapse firing. A signal arrives, gets scaled by the strength of that connection, and passes on. Same operation. And here, I have to break something you'll hear repeated everywhere. Firing a synapse is not cheap. It costs around 10 picojoules, about 160,000 molecules of ATP, the fuel your cells run on. 10 picojoules. The chip's multiply cost 2/10 of one. So on raw arithmetic, silicon doesn't just win, it wins by about 50 to 1. Your neurons are, operation for operation, dramatically worse than a transistor. So why is the brain the one running on 20 watts? 2 reasons, and neither is that biology has better hardware. 1. The brain never goes and gets anything. In your head, the weight and the calculator are the same physical object. The synapse is the number, and it does the multiplication itself, right where it sits. There is no trip, because there is nowhere to go. The chip pays 64 picojoules of delivery on every weight. The brain's delivery cost is 0. Not small, 0. The concept doesn't apply. 2. Almost none of it is switched on. At any moment, between 1 and 5% of your neurons are doing anything. The rest are silent, and silent is free. An AI model does the opposite. For every single word, it wakes every weight it has, all 70 billion, even the ones with nothing to do with your question. Imagine reading an entire library, cover to cover, to answer one question, then doing it again for the next word. Here's the good part. Every one of those tricks already exists in silicon, not as science fiction, as shipping products. Let's switch them on and watch the bill. 1. Stop waking the whole network. Split the model into specialists and wake only the relevant ones. The industry calls it mixture of experts, and nearly every frontier model now uses it. It is, straightforwardly, a copy of your cortex. 2. Get rid of the clock. A normal chip has a heartbeat. Hundreds of millions of transistors flip every tick, whether or not there's anything new to say. A neuron spends nothing until a signal arrives. Intel builds a chip that works this way. So does IBM. In our simulation, this alone removes the 85% of energy burned by a chip sitting powered on, doing nothing. 3. The big one. Put the calculator inside the memory. Stop moving weights to the processor. Make the memory cell do the multiplication, exactly like a synapse. Cerebras already builds a processor the size of a dinner plate, specifically so every weight can live on the chip and never leave. Watch that bar. That's the warehouse being demolished. 4. Stop being so precise. A synapse holds maybe 4 or 5 noisy bits and fails to fire half the time. It works anyway. Nvidia's newest chips compute in 4-bit numbers for exactly this reason. 5. Build upwards. Your brain is a volume. Nothing is far from anything. A chip is a flat sheet. Stacking memory in 3 dimensions is, literally, shorter wires. All 5 on real hardware numbers. Energy per word falls by more than 400 times. So why don't we just build that chip? One unsolved problem. And it's worth being straight. We know how to run a neural network on this hardware. We don't know how to train one. Training needs precision and reliability. An analog, event-driven hardware is bad at both. The brain uses local learning rules we still don't understand. But the lesson isn't the brain wins. The lesson is that the toll is optional. For 70 years, we've built computers with memory in one place and the calculator in another. Because in the 1940s, that was sensible. Everything since inherited that decision, including the machine running the most advanced AI on the planet, which spends most of its energy on shipping and handling. Your brain never made that choice. It has no warehouse. Memory and maths in the same place, and it gets away with 20 watts. Everything here came out of a simulator I built on published specifications and peer-reviewed neuroscience. Link below. Change the chip, change the model, flip those 5 levers yourself. Go find out how much of that $30,000 chip you can actually wake up.